MegaCorp's procurement. A P I just fell over. A flood of requests hammered the database. The monolith backed up, and everything went down together. Amazon Web Services gives you 3 services that all look like the fix, and they overlap just enough that picking the wrong one takes the whole system with it. Cloud Architect Path, Episode 14. Stack Lessons Rolling. By the end of this video, you'll know exactly when to reach for SQS, when to reach for SNS, and when EventBridge is the only right answer. Understanding which service fits which scenario is a foundational resilience skill, and it often comes down to a single word in the scenario. Before we get into the mechanics, let's pin down 5 terms you'll hear throughout this video. SQS is a message queue that buffers work between a producer and a single consumer. SNS is publish and subscribe, one message pushed to a topic, copied to every subscriber at once. EventBridge is a serverless event bus that routes each event by its content. Fanout is the pattern where one message reaches many consumers in parallel. And Kinesis data streams is a replayable stream where multiple independent readers can each draw from the same data. Keep those 5 straight and the rest of this falls into place. Here's the core problem. A monolith fails as a single unit. When one component slows down, the whole request path backs up behind it because everything shares the same thread of execution. So when a surge of procurement report requests hits MegaCorp, those slow report queries drag down the database and the entire API stalls, even the parts that had nothing to do with reports. The root cause is that producers and consumers are tightly bound together. The thing generating the work and the thing doing the work can't scale separately, and they can't fail separately either. One slow piece takes the whole system with it. The remedy is decoupling. You put a buffer between the producer and the consumer, so neither one has to wait on the other. The producer drops its work off and moves on immediately. The consumer picks up work at whatever pace it can handle. Now the 2 sides scale independently, and just as importantly, they fail independently. A slow consumer no longer topples the producer. That single architectural move is what turns MegaCorp's fragile monolith into something that bends under load instead of breaking. So which buffer do you reach for? Here's the whole map in one picture. SQS is a point-to-point queue. One message goes to one consumer. That's your simplest buffer. SNS is publish and subscribe fan-out. One message copied to many subscribers at once. And EventBridge is a content-based event router. It reads what's inside each event and routes it across many services accordingly. Same underlying problem, 3 different shapes. We'll take each one at a time. Let's start with SQS, the simplest decoupler of the 3. It's a fully managed queue that stores your messages redundantly across multiple availability zones, so you're not babysitting any servers. The flow is dead simple. A producer drops a message onto the queue. A consumer pulls it off, processes it, and then deletes it. That delete is important. Once the work is done, the message is gone. Now apply that to MegaCorp. When the procurement spike hits, each report request becomes a message on the queue. The queue fills up and a fleet of workers drains it at their own pace. The API itself returns immediately because all it did was drop a message. It never waits on the slow downstream work again. Picture a diner's order ticket rail. The waiter clicks each order to the rail and heads straight back to the floor. The kitchen pulls tickets off one at a time and cooks each dish. When the lunch rush hits, the tickets pile up on the rail, but they never back up into the dining room, and the waiter never stands around waiting for the kitchen. That rail is your queue. It absorbs the surge so the front of the house keeps moving no matter how slammed the kitchen gets. SQS comes in 2 flavors, and the difference between them is a favored exam discriminator. Standard queues give you at least once delivery, which means a copy of a message might occasionally arrive more than once. Ordering is best effort, so messages can arrive slightly out of sequence. In exchange, you get nearly unlimited throughput. Because duplicates are possible, your consumers need to be idempotent. Processing the same message twice must be harmless. FIFO queues flip the trade. They give you exactly once processing and strict first-in, first-out ordering. The cost is throughput. 300 messages per second by default, or 3,000 with 10 message batching, or up to 70,000 with high throughput mode enabled. If you need exactly once processing and strict order, FIFO is the answer. The SQS developer guide puts the FIFO guarantee plainly. FIFO queues are designed for when the order of operations is critical, or where duplicates can't be tolerated. The order in which messages are sent and received is strictly preserved, and a message is delivered once and stays unavailable until a consumer processes and deletes it. Think of a bank's payment processor, where a debit must never be applied before the matching deposit. That strict order and that guarantee against a double charge is exactly what FIFO exists to protect. So here's the decision rule to carry into a scenario. Ask yourself 2 scenarios. Does the order of messages truly matter? And would a duplicate cause a real business error? If the answer to both is yes, you need FIFO. If duplicates are tolerable and throughput matters more, choose standard and make your consumers idempotent. In practice, idempotency is cheaper than the FIFO throughput ceiling, so standard is the default starting point. And remember, you cannot convert a standard queue to FIFO after you create it. That choice is locked in at creation. Quick recap before we move on. SQS buffers work between a producer and a single consumer group. One message, one consumer. Standard gives you high throughput, but it's at least once and only loosely ordered, so your consumers must handle the occasional duplicate. FIFO trades that throughput away in exchange for strict ordering and exactly once processing. That's the whole SQS story. Now, what if you need one message to reach several different services at once? That's where SNS comes in. SNS is publish and subscribe. You make a single publish call to a topic, and SNS pushes an identical copy of that message to every subscribed endpoint simultaneously. Those subscribers are flexible. An endpoint can be an SQSQ, a Lambda function, an HTTP endpoint, an email address, or even SMS. And the keyword is push. Subscribers don't poll for updates and they don't coordinate with each other. None of them even knows the others exist. One publish, and everyone who's listening gets the message at the same moment. Think of a stadium public address system. One announcer speaks once into the microphone, and every section of the stadium hears the exact same message at the exact same time. The announcer doesn't call each section individually, and the sections don't talk to each other. That's NS, one publish, broadcast to everyone at once, with zero coordination between the listeners. Now watch what happens when you combine SNS with SQS. This is the flagship decoupling design, so follow the flow. On the left, an order-placed event gets published once to an SNS topic. From that topic, SNS delivers a copy to 3 separate SQs queues, an inventory queue, a billing queue, and an analytics queue, all at the same time. Each queue then feeds its own independent worker, draining at its own pace. One publish, 3 durable copies, 3 consumers that never touch each other. So I bolt a queue onto each subscriber instead of subscribing the services directly, because each layer does a distinct job. SNS provides the real-time push-to-many layer. That's the fan-out. Each dedicated SQ then adds durability and back pressure for its own consumer. Here's why that matters. If the analytics service is slow or temporarily down, its queue simply holds the messages until it recovers. Inventory and billing keep processing, completely unaffected. Now contrast that with SNS on its own. SNS is push only with no storage. If a subscriber is offline at the moment, SNS publishes, that message is gone. The queue is what turns a fragile broadcast into a durable, independent pipeline for every consumer. Amazon Web Services spells this out in the SNS Developer Guide. When you pair SNS and SQS together, messages can reach applications that need immediate notification, and the same messages can also land in an SQS queue for other applications to process later at their own pace. That captures the whole point. SNS handles the immediate notification side. SQS handles the durable process when ready side. Neither service does both jobs alone, which is exactly why the combination is the canonical decoupling design. So lock this in. When a scenario says one event must trigger several downstream services, the answer is an SNS topic with one SQ per subscriber. Not a single SQ that all the consumers share. That would deliver each message to only one of them. The fan-out pattern gives every service its own durable copy. This is the design to reach for the instant you see one-to-many with independence. That brings us to EventBridge, the third and most intelligent tier. EventBridge is a serverless event bus that receives events from Amazon Web Services, your own applications, and SaaS partners. Here's the part that sets it apart. Rules match on any field inside the event payload, the source, the type, or a nested detail value. That means one event can go to completely different targets depending on what's inside it, not just where it came from. And crucially, the producer never knows what will consume its events. It just emits them onto the bus, and the rules decide where they go. That's the deepest form of decoupling of the three. Picture a postal sorting facility that routes packages by reading the contents label, not just the address. A package marked hazardous goes to a special handler. One marked express bypasses the standard belt. An international package gets pulled aside for customs. All of that from a single drop-off point, decided entirely by what's written on the label. That's content-based routing. EventBridge reads inside the event and sends it down the right path automatically. Here's what a rule actually looks like. This event pattern matches only events from the order source of type order created, where the priority is critical and the type is infrastructure. Notice it's reaching inside the nested detail fields, not just looking at the origin. When an event satisfies every one of those conditions, EventBridge fires it at the configured targets. Here, a Lambda function that spins up and a PagerDuty incident. Change one field in the incoming event, and it takes a different route entirely. That's the whole idea. The content decides the destination. EventBridge has one edge that neither SNS nor SQS can touch: native SaaS integration. It ships with more than 45 pre-built partner event sources, including Zendesk, Datadog, Salesforce, Stripe, and Shopify. Those partners push their events straight into a dedicated partner event bus in your account. No polling, no custom webhook plumbing. So a critical Zendesk ticket can trigger a Lambda that pages your on-call team, all through native wiring. On top of that, the schema registry can auto-discover the structure of events flowing through your bus and generate typed code bindings for your IDE. The takeaway for a scenario is simple. The moment you see a SaaS product name, that's EventBridge territory, SNS and SQS have no native SaaS integrations at all. SNS and EventBridge can look similar, So let's draw the line clearly. SNS, broadcast to all subscribers. It does support optional per-subscription filter policies, and it delivers the highest throughput fan-out of the two, but it has no SaaS integrations. EventBridge, by contrast, routes by content matching rules rather than broadcasting. It brings us 45+ SaaS partner sources, a schema registry, and event archive and replay. A single rule can fan out to up to 5 targets. The short version, choose SNS for high-volume broadcast to endpoints you control, and choose EventBridge when routing depends on event content or when a SaaS product is involved. Let's recap the middle of the video. S sends one message out to many subscribers by push with no polling. Pair it with SQS and you add durability, so a slow or offline consumer holds its own backlog without blocking the others. EventBridge steps up a level and routes by the content of each event, and it's your answer whenever SaaS integration is in the picture. Now for the distinction that trips up more people than any other in this domain. Here's SQS versus Kinesis data streams, and this is where careful reading pays off. With SQS, a message is deleted after it's consumed. It serves one consumer group per message. There's no replay of anything in the past, and it's the simplest model for buffering a task queue. Kinesis is a different animal. Data is retained in the stream, 24 hours by default, up to 365 days if you configure it. Multiple independent consumers can each read the same data at their own position. You can replay from any point in the stream, and ordering is preserved within a shard. We'll go deep on Kinesis in a later episode, but the contrast you need right now is retention and replay versus consume and delete. Picture a conveyor belt sushi restaurant versus a river. At the sushi belt, each plate is grabbed by one diner, and it's gone from the belt forever. That's SQS. A river is different. It keeps flowing whether or not anyone is fishing, and multiple fishing spots along the bank can each draw from the water independently. If you want, you can walk back upstream and fish the same stretch again. That flowing, replayable mini readers picture is Kinesis. Same water, many independent draws, nothing consumed away permanently. This is the mix-up that costs the most points. If a scenario describes multiple independent services each needing to read the same events, or it mentions replaying or reprocessing past data, SQS is the wrong answer. SQS physically deletes each message after one consumer reads it, so it can't hand the same message to 3 separate consumers. The word replay is Kinesis's exclusive signal. No SQS answer will ever involve replaying past messages. See replay or multiple independent readers, and you reach for Kinesis, or you fan out with SNS. See a simple task buffer where each item is processed once, and it's SQS. Now let's turn decoupling into a concrete resilience payoff with auto-scaling. The instinct is to scale your consumer fleet on CPU, but CPU tells you nothing about how many messages are actually waiting in the queue. A worker can sit at low CPU while thousands of messages pile up behind it. The better signal is queue depth. When MegaCorp gets a 10-time spike in procurement reports, tracking the backlog lets the fleet scale up in minutes to drain it, instead of the API toppling over. Worker count grows to match real demand, not processor load. But there's a subtlety, and Amazon Web Services calls it out directly. The EC2 Autoscaling Developer Guide warns that the raw number of messages in the queue might not change proportionally to the size of the autoscaling group. In other words, tracking total queue depth by itself doesn't scale cleanly, because as you add workers, that raw number doesn't respond in a way that tells you whether you have enough capacity. The guide solution is to use a backlog per instance metric, with the target value being the acceptable backlog per instance to maintain. So you don't track the total, You track the backlog divided across your workers. Here's the formula in 2 parts. The top box is your metric. Backlog per instance equals the approximate number of messages in the queue divided by the count of in-service instances. That's how much work each worker currently faces. The bottom box is your target. Take the latency your application can accept and divide it by the average time one instance takes to process a single message. That gives you the acceptable backlog per worker. Feed both into a target tracking policy, and autoscaling keeps adding or removing workers to hold that ratio. And a modern tip, you can compute this with CloudWatch metric math directly, instead of publishing a custom metric with your own script, which cuts cost and complexity. And that's the real insight. Queue depth per worker measures the actual business problem, how long it will take to clear the backlog, in a way that CPU never can. CPU is a lagging, indirect signal. Backlog per instance is the leading indicator that maps straight to your latency target. This is the concrete payoff of decoupling. Because the work sits in a queue, you can measure it, and because you can measure it, you can scale to meet it precisely. Before the cheat sheet, here's the mental model that ties it all together. In a large system, these 3 often stack rather than compete. EventBridge sits at the top as the intelligent router, matching on event content and source to decide what's relevant. SNS sits in the middle, fanning a relevant event out to many consumer groups at once. And SQS sits at the bottom, giving each consumer durable, independent buffering. Not every architecture needs all 3 layers, but understanding where each one adds its distinct capability is exactly what separates a right answer from a plausible wrong one. So here's the cheat sheet to carry into every question. 1 consumer plus buffering plus the word simplest points to SQS standard. No duplicates or strict order points to SQS FIFO. Notify many endpoints or broadcast points to SNS. Content-based routing or any named SaaS product points to EventBridge, and replay or multiple independent readers points to Kinesis. Read the scenario, find the qualifier, and match it to one of those 5 lines. Now let's see how well it sticks with a quick 5-question quiz. Let's test what you've learned. Question 1. An e-commerce platform needs a single order-placed event processed independently by 3 separate services: inventory, billing, and analytics. And a slow analytics service must never delay the other 2. Which architecture fits? Option A, a single SQS standard queue that all 3 services pull. Option B, an SNS topic with 1 dedicated SQS queue subscribed per service. Option C, an SMS topic with all 3 services subscribed as direct HTTP endpoints. Or option D, a single SQL queue shared by all 3. Lock in your answer before I give it away. This one is B. An SNS topic fans the event out to a dedicated SQ for each service. Every consumer gets its own durable buffer, so a slow analytics service only ever holds up its own queue. A single shared queue would hand each message to just one of the 3, and direct HTTP endpoints would lose messages whenever a service was offline. Question 2. A SaaS analytics platform ingests events that must be read independently by a real-time dashboard, a fraud detection model, and a data lake delivery stream. After a failed model deployment, the engineers need to reprocess the last several hours of events. Which service should carry this data? Option A, Kinesis data streams. Option B, an SQS standard queue. Option C, an SQS FIFO queue. Or option D, an SNS topic with email subscriptions. Think about which constraint matters most here. The right call here is A, Kinesis data streams. 2 words in the scenario decide it: multiple independent readers and reprocess. Kinesis retains data in the stream, lets each consumer read at its own position, and supports replay. Any SQS option is out because SQS deletes each message after it's consumed and can never replay it. Question 3. A team wants an EC2 autoscaling group to scale its SQS consumer fleet so the backlog clears within an acceptable latency. Which scaling signal should the target tracking policy use? Option A, average CPU utilization across the fleet. Option B, the raw approximate number messages visible metric as a direct target. Option C, a backlog per instance metric, messages divided by the in-service instance count. Or option D, the number of SAA-C03 calls per second. Run the decision rule from earlier before you answer. It has to be C, and here's why. Amazon Web Services documentation explicitly warns that raw queue depth doesn't change proportionally to the size of the auto-scaling group, which rules out option B. CPU is a lagging, indirect signal and send rate measures producers, not backlog. Backlog per instance, messages divided by in-service count, is the metric that maps straight to your latency target. Question 4. A payment processor must guarantee that debit and deposit messages for the same account are processed in the exact order they were sent, and that a retried send never causes a duplicate charge. Which SQS configuration is required? Option A, a standard queue with idempotent consumers. Option B, a standard queue with a dead letter queue attached. Option C, a FIFO queue with high throughput mode enabled. Or option D, a FIFO queue using message druid per account with content-based deduplication. Got your pick? Let's see. If you said D, well done. The scenario demands both strict per-account order and protection against duplicate charges, which is exactly the FIFO promise. Setting message GRUD to the account number preserves ordering within each account, and content-based deduplication stops a retried send from charging twice. Standard queues can't guarantee order, and high-throughput mode alone doesn't address the per-account grouping. Last question. A DevOps team wants a critical Zendesk ticket to automatically trigger a Lambda function, but only when the ticket's priority field is critical and its type is infrastructure. Which service should route this event? Option A, EventBridge with a content matching rule on a partner event bus. Option B, SNS with a topic subscribed by the Lambda. Option C, SQS with a Lambda polling the queue. Or option D, Kinesis data streams with an enhanced fan-out consumer. Pause here if you want more time. The answer is A. 2 signals point straight at EventBridge. First, Zendesk is a named SaaS product, and it's a native EventBridge partner event source. SNS, SQS, and Kinesis have no SaaS integrations. Second, the requirement filters on nested fields, priority and type, which is exactly what EventBridge content matching rules do. It routes only the qualifying tickets to the Lambda. And we've wrapped decoupling architectures, SQS, SNS, and EventBridge. Hit subscribe so the rest of the Cloud Architect path comes to you automatically, and so YouTube shows these to more learners. I read every comment, so share what helped and what didn't. Want me to build a series on a different certification? Drop it below. And if anything about the style or the speed could improve, I genuinely want to hear it. Next lesson soon.